Hi everyone, welcome back to our series on statistics. This is episode number 3 and we'll be dissecting random variables. In this episode, we'll be dissecting 4 major topics. Firstly, we first got to understand the difference between the 2 types of variables, deterministic and random. Then we investigate the 2 categories of random variables, discrete and continuous. Thirdly, we learn everything about discrete random variables, the notation, formula, and properties. And finally, everything about the continuous random variables. So to understand what a random variable is, let's first understand what a deterministic variable is. Deterministic variables only have one outcome for an event. In other words, an input directly maps to only one output. This sounds very familiar, right? Our good old functions can be thought of as deterministic because we substitute one x value into the function machine and it poops out one y value. So given a function f of x, if we knew what the x value is, then we can determine what the y value or the outcome would be with certainty. However, in most real-life situations and experiments, outcomes are random. Hence, random variables have more than one possible outcome for each event. So inputs map to multiple outputs, and we can write down the probability of each outcome occurring. Now, there is just one disclaimer about using random variables in statistics. They have to be numerical or have a numerical value assigned to each outcome because we want to work with quantitative variables to specify distributions or calculate summary statistics, as we will encounter in future episodes. So variables can either be deterministic or random. And random variables can be further split into 2 categories, discrete and continuous. For our purposes, we have very simple definitions. A discrete random variable has a finite number of possible outcomes. For example, outcomes of a die roll. There is a specified set of outcomes ranging from 1 to 6. A continuous random variable has an infinite range of possible outcomes. For example, heights of students. If you think about it, there are technically an infinite number of heights that are possible. There are infinitely many fractions and decimals already just between 2 integers. Now, for the excelling students out there, there is a legit formal definition, but please note that countability is outside the scope of the syllabus. So let's look at an example of a discrete random variable. When we first start any question, we must define what the random variable is. So let's write, let the random variable x be the outcome of a loaded die. Now, we want to construct a table of values for our random variable. Fun fact, we conventionally label random variables in uppercase, so we have capital X. Possible outcomes are then labeled as lowercase x. Now we fill in the associated probabilities of each outcome happening. That notation just means, what is the probability p of the random variable capital X equal to a certain outcome little x? So in our example, we're spicing things up and using a loaded die, so note that probabilities are not all equal to 1 on 6. Like cumulative frequencies we learnt in episode 2, cumulative probability is the sum of the probabilities from the start to the current outcome. Hence, that notation just there just means the probability of the random variable capital X being less than or equal to the current outcome x. If we can somehow express the probability of each outcome as a function, wouldn't that be nice? A function that expresses the associated probabilities of a discrete random variable is called the probability mass function, or PMF, denoted little px. So in our example, we can both deduce and graph our PMF to be x on 21. Similarly, if there exists an expression that describes the cumulative probabilities, we call that the cumulative distribution function, CDF, and denoted capital F of x. Because the PMF represents the probability of each outcome and the CDF represents the cumulative probability, we can immediately establish a relationship between the PMF and CDF. Hence, the CDF is just equal to the sum of the PMF from the start to the current outcome. Graphically, we can visually observe that the CDF represents the cumulative area of the columns in the PMF. Now, there is one intuitive property around total probability. What is the sum of probabilities of all outcomes? It's 100%, so if we add every single probability in the PMF, it should equal to 1. Similarly, what is the cumulative probability of the last outcome B? The CDF at B is just the sum of probabilities from the start to the last outcome, which again is equal to 1. Now, a classic question is to prove that a certain probability distribution is a valid PMF. To answer this, we just need to satisfy two conditions. Firstly, it needs to satisfy the total probability condition, so prove that the sum of the PMF is equal to 1. Secondly, every probability needs to be positive, so prove that the PMF is always greater than or equal to 0. Another classic question is to find the probability of a range of outcomes. To calculate probabilities between outcomes C and D, you can either physically add each probability of the PMF from C to D, or you can use the differences in CDF. Since f of D is the probability from A to D, and f of C minus 1 is the probability from A to C minus 1, by taking the difference of the two CDFs, we can obtain the probability between just C and D. Now, in our example of a continuous random variable, we again need to define what the random variable is. So, let the random variable x be the length of the fish caught. Unlike a discrete random variable, we don't need to construct a table of probabilities because there are infinitely many outcomes. Now, this one's going to be confusing, so watch out. Because there are infinitely many outcomes, the probability of a specific outcome occurring is always equal to 0. However, do you agree that some outcomes can be more likely than other outcomes? So we can find the likelihood of an outcome relative to other outcomes, which is called the probability density. To simply put, a probability density is not a probability. We cannot calculate individual probabilities from the PMF, but we can calculate the range of probabilities from the PDF. The function that describes the probability density is just called the probability density function, PDF, denoted little fx. In almost all cases, you'll be given the PDF in the question, and you can also graph this example PDF. Note that this PDF is a smooth curve, whilst the PMF is a histogram. The function that describes the cumulative probabilities is again called the CDF. We just need to add up the many densities continuously from the start to the current outcome. As we will visit in the integration series, to add continuously is to integrate. That's why rather than using sigma, we just integrate the PDF from A to X to obtain the CDF. Graphically again, the CDF represents the cumulative area under the PDF. We can deduce similar properties about a continuous PDF and CDF based on the fact that the sum of all possible probabilities are equal to 1. For calculating range of probabilities, we again just need to integrate the PDF over that interval, or we subtract the CDFs directly this time because we are looking for the area between C and D. So subtracting f of D to f of minus C gives us the exact area and the range of probabilities between C and D. So now we have a wealth of properties for both discrete and continuous random variables. So that's it for episode number 3. Tune in for the next episode to use these random variables to calculate summary statistics, or click here to watch episode 0 on the big picture of statistics. So like, subscribe, leave a comment below on what you would like to learn in the future. I'll be there.